Yeah, I'm not sure this was clear from the announcement. So yesterday this was supposed to be a separate seminar, and now I'm starting some lectures where I hope to introduce the Yangian algebra on a really basic level. And yeah, in principle, I would have prepared material for 4 times 60 minutes, but yeah, I don't know how long things take with questions, and yeah, let's see. So yeah, the idea for the plan for these lectures is written here, so it's divided into 4 different parts, and I will really start with a very basic, some very basic statements about classical integrability in 2D field theory and how non-local symmetries arise there. Only then I will introduce the Yangian algebra and discuss some more mathematical aspects of it. Then I will make some comments on how to quantize these charges in the 2D field theory, and finally I would make some comments on how these non-local symmetries and the Yangian appears in the ADS-CFT duality. So let me start with this first chapter here, and before I say anything about non-local symmetries, it's probably good to first say something about local symmetries. To distinguish what I mean by this. So the standard approach to symmetries is that you have a Lagrangian that depends on some fields and their derivatives, and you consider a symmetry transformation delta phi that leads to a variation of the Lagrangian being just a total derivative, and typically this leads to a conserved Noether current J mu, which, yeah, being conserved is simply this statement here. And yeah, then you integrate the 0 component of this current. If I'm now in 2 dimensions, it's just a single integral, and this gives you a conserved charge. And here I integrate over the whole infinite line. And this charge is indeed conserved if the current is conserved. So I get something like this. I can use the current conservation to write things in terms of this derivative here, and I get 0 under the assumption that this current vanishes at the spatial infinity. So this is for j of t plus minus infinity being 0. So this is just the standard approach to local symmetries and their charges. So let's look at a concrete example, namely Lorentz transformation, or more precisely a Lorentz boost. So I want to do some transformation of this form. If I have a scalar field, it would look like this. And this yields some conserved currents. So this is a generic Lorentz transformation which have this form. And this is the energy momentum tensor. Yeah, so in principle these are this gives me several currents depending on what I choose here. If I'm in 2 dimensions, and I choose rho to be 0 and sigma to be 1, then I really have the boost. And the boost charge is given by this integral here, dx t t01 y minus x t00, and this is here just the Hamiltonian density in my theory. So I want to specify this even further to the case of t being 0. So this charge at 0 time is given by this. Yeah, so this simply drops out. This is the x times the Hamiltonian density. And now I just want to slightly rewrite this here by blowing up this x into an integral. So I write an integral over dx, and I write an integral over dy, h of x. And here I will have something like infinity times the conserved energy. I just want to say, say that I can schematically write things in this form. In principle, to get rid of this divergence here, I would have to regularize this expression by antisymmetrizing things. But yeah, just schematically, let's say I get this expression plus some extra term which would also be conserved. So in some sense, I can write this conserved charge associated to the Lorentz symmetry as this integral here, yeah? And I've done this because formally I want to understand this now as a bilocal integral, yeah? So you see that instead of having just a single local integral, I formally wrote this as a bilocal integral. Of course, this is very formal because one of the integrations is really trivial. I just get the x from it. But yeah, if I want to draw a picture of this, I could perhaps, of this integral, I could perhaps write it like this. So I have the space dimension, and now I have some density sitting here, h at point x, and I have another density sitting here at point y, and this is, in this case, simply the identity, yeah? So I could just insert a 1 here, and this corresponds to the second integral. And well, this particular ordered integral, let me just denote it by this line. So I have formally an expression that that is an integration over two such densities. Yeah, so I've done this for the standard Lorentz boost, and what I want to do now is to introduce symmetries which have a non-trivial second leg here. Yeah, so which have two densities on both of these sides. And this is why I already formally wrote things like this, and it's probably not a coincidence that I can do this for the boost, because the boost plays a particular role also in the context of these higher non-local charges and the Yangian symmetry, as I will also introduce in the following. So let's come now to honest. Sorry? Well, for the Lorentz symmetry, it's not necessary, but this picture, for this picture, I think it's necessary, right? It's the same as as I would show for the Yangian generators. It's clear how to formulate this in 2 dimensions, but it's not so clear how to lift the statement. You need this 1 dimension. Yeah. Yeah? And this is also why I'm starting here with this 2-dimensional picture, because this is really the natural world where these higher local charges live. It's 2-dimensional field physics. Yeah. So Let me now talk about bilocal symmetries, in particular internal symmetries. And what I want to do is to assume that I have such a local current, a local conserved current, as I've written down before. Now not like the Lorentz current, but rather the current of an internal symmetry. And this current should be conserved. So I should have del mu, J mu being 0. And it should be flat. Conserved and flat. And flat, by flat I simply mean that this expression here, so 0 and 1 now corresponds to the time and space component. That this is 0. So I assume an additional condition for this current. And since this is an internal current, I would like to assume some underlying symmetry algebra. So I can decompose this current into the generators of this algebra, which obey some Lie algebra commutation relations. And I won't distinguish here between upper and lower indices during these lectures. Yes?
Flatness condition and geometric condition on some bundle.
Probably.
I mean, what is the bundle for which these J's are to the third order connection, and that is flat? Is the coincidence that the condition just turn out to be something that we're familiar with from the?
No, it's certainly not a coincidence. No.
Yeah, but what? Usually that is the gauge field, right? Yeah, usually it's the gauge field. I don't know. Yeah.
No, well, integrability is a geometric property, I would say. So no, this is the flatness that you know, I guess. Just
Usually we're familiar with the gauge field being flat, not currents being flat, right? Because the gauge field being flat is just a statement about the bundle on which the gauge field is the connection, and it just says that parallel transport doesn't do anything. But I don't think of using the current to parallel transport anymore. Right.
Well, I think it parallel transports the solution to an auxiliary problem. I will comment on this. Yeah, I will comment on this a bit later, actually. But yeah, I'm not sure it's obvious how this is interpreted in a physical way. It's maybe in this sense it's a coincidence. I will comment on this later.
And the concept of the ON sigma model, where this current corresponds to this nominal charges corresponds to 4 minor charges. There the first level counts are the inverse layers.
Yes.
So where so the first one, then of course it considers tau as charges, for which it just follows by some kind of a but yeah, I also have always wondered this flatness how. So I really don't know. Apart from this, the sigma modeling context, where.
Sure, this is a particular example where it nicely connects to geometry, but yeah, at the moment I don't want to make any assumption on the model other than having such a current. Yeah, it should be enough to have integrability equivalent. No, well, at strong coupling certainly there is. Yeah, because there you have a coset model which is very similar to this this ON sigma model. At weak coupling, it's not. Yes, yes, you have this.
And this, I think, thought about giving a lower.
Yes. There you have a two-dimensional field.
This is what makes the photonic spectrum interesting for because for S5 it's just the standard story, and for ADS5 you can just make some changes of mind here and there to make the whole thing kind of so interesting on ADS5. You can
So, yeah, at strong coupling, this is essentially what's behind the integrability here. Because it's a 2D field theory. Okay.
Also, when we talk about things being flat, one can also talk about cohomology, right? I mean, one way to make this flat is just think of it as a gauge field, where the worst case, like you say, it's pure gauge, right? The inverse is G. But can it be not pure gauge and still be flat? I mean, does the cohomology play any role?
I guess I don't know. I don't have an answer for this. Okay, here I just want to make these two assumptions, conservation and flatness. And now I want to write down a new current. So I want to define a bilocal current which I call J hat, and which is given by this expression. So epsilon is just the antisymmetric tensor, and here I write down a particular combination of these local currents. Yeah? So at the moment I simply define this thing and I want to show that given these assumptions there, this is indeed also conserved. So let's compute this derivative here. What I get is del mu epsilon mu nu j nu a of x minus, well, maybe I don't write this down. So I have one contribution where the derivative here acts on the current in front, but this is conserved, so this will not contribute. And then I have another one where the derivative acts on the integral. Yeah? And the action on the integral is, so now I sometimes write only x instead of t and x just to be a bit shorter. And I can summarize the action on the integral as this thing here. Either I act on the current here, then I can use current conservation to rewrite things, or I act on the x. And this gives me this sum here, depending on whether I have the 0 or one component of the derivative. Yeah. Okay, and now I can simply rewrite this. And the nice thing is that this turns out to be exactly the flatness condition that I assumed to hold. Yeah, so you see that if I have a current which obeys these two conditions, then I can define a bilocal current of this form which is also conserved. So this j hat mu is conserved. And as before, I can also write down the associated charge. a bilocal, or let me call it level 1. Charge, which I call capital J hat, and which is just the integral over the 0 component of this current. And I can write this in this simple form. I just spell it out explicitly because the form is essentially what will define the Yangian level 1 generators later. Yeah, and now you see that similar to the picture I've drawn before, I can understand this here as some density JB sitting at point X and some density JC sitting at point Y, and I have again this weird bilocal integral here. Yeah? So the structure is similar to this Lorentz boost I've shown you, just that now I have a non-trivial density sitting on one of the two legs. And again, this charge is conserved if I assume that the current is 0 at plus and minus infinity. So, of course, this approach is a bit ad hoc. I made this assumption. I wrote down this current whose form is maybe not so easy to guess. So it would be nice to have a slightly more systematic approach.
Is the level one also flat?
No, it won't be flat. No. So one question is, what's the system behind constructing this charge? And the other question is there actually only one higher charge or are there more? So let's try to see if we can get a whole tower of non-local symmetries. And let's try to approach a more systematic understanding. And let's introduce a covariant derivative. Which has this form. And now the conservation of J mu is simply the statement that the partial derivative commutes with this when I contract the two indices, and the flatness means that d nu is 0. Yeah, and what I now want to do is an induction. So let's assume we have a current of level n, given J mu n, which is conserved.
Sorry, can you repeat what you're trying to do now? What you're trying to do now?
I try to reformulate the statement, again in a bit different way. I introduce this into this covariant derivative. I make these two assumptions, which correspond to the previous assumption of conservation and flatness. And now I want to argue that if I have one current of level n, I can construct a higher current. And then I will tell you how this starts.
So just to make sure, so level 1 current to be conserved, you require level 0 to satisfy some flatness condition, right?
Yes?
For level 2 to be conserved, you don't require level 1 to be flat.
No. I think you will see from this construction how it works. Yeah. So I assume a current of level n that is conserved, and then there exists a potential chi n associated to this current such that I can write the current as epsilon mu nu del nu chi n, and here I assume n greater equal 0. Yeah. So if the current is conserved, I can write the current using such a potential as a derivative of this potential. And now I want to define a current of level n plus 1 using this potential, namely setting it to be d mu, now capital D mu, this covariant derivative acting on the potential. So why have I done this? One side remark. So I have another condition in addition to this 1 and 2 here that I want to use, namely that the derivative of this potential chi n can be written in the following way: epsilon mu nu j nu n, and this I get from this. So I act with epsilon mu nu on this equation. I use that the square of epsilon is basically delta, and then I can express the derivative in terms of this. Yeah, and this I can write as epsilon mu nu d nu chi n minus 1, simply using this equation here. Yeah, so this is something I want to use. And now I want to show that the new current, the level n plus 1 current, is actually conserved. So I compute del mu j mu n plus 1, which is del mu d mu chi n. And using my condition 1, which is the conservation, namely that these two commute, I can write this as d mu del mu chi n using what I derived here. I can now replace this by this. So I have d mu, epsilon mu nu d mu d nu chi n minus 1. Yeah, and now using 2, namely that these covariant derivatives commute, and here they are contracted with the antisymmetric tensor. This means that I get a 0 here, yeah? So given a level n current, I can construct a level n plus 1 current in this way. That's conserved. This is like? Yes. Now I'm in 2 dimensions, so you mean a circle, yeah? Well, I have this assumption that at infinity the current is 0. So yeah, this is actually the problem with the boundary conditions. You can do similar things, but I guess you can generalize this, yes. But yeah, I haven't thought about this concretely yet, so there may be subtleties. Okay, here I just want to show that based on these assumptions, I can actually get a whole tower of.
The flatness that you can use is only for that level
Yes.
0.
Yes, flatness only for level 0, exactly. So connecting to what I had before, what's my start of this induction? I can simply choose the potential chi of -1 to be 1 with a current J mu -1 being 0. And then this implies that I have a current J mu 0, which is exactly the current I started with, my level 0 current, which is epsilon mu nu del nu chi 0. And here, if I want to write down explicitly what this potential is, it's just the integral minus infinity to x dy j naught of y. And yeah, this is the starting point for this whole induction. So I have one current which is conserved in flat, and this implies now an infinite tower of non-local currents and charges.
In interesting topology, then there will be questions of cohomology because we are assuming that there are you can replace that by potential.
Yeah, yeah. Mm-hmm. Yeah. Okay. So having an infinite tower of non-local symmetries is roughly here what I want to understand as my definition. Well, it's always hard to define integrability properly, particularly if you have infinitely many degrees of freedom, degrees of freedom. But here, this infinite tower of conserved charges I want to understand as my definition of integrability. So given these simple assumptions that I have a current that's local current that's conserved and flat, I can actually in 2 dimensions construct in this way such an integrable model.
So the chi one takes a bit similar way I construct. The chi 0 you construct out of J0.
Yes.
Chi 1 I construct out of J1.
Sorry, the 0 is
J.
This is just the time component here of it's true, of J0. So it's 0, 0. Yes, I would construct it out of J1 then, yes.
And the J mu there is the J mu of the J0.
Yes, exactly. That's exactly here the same thing. This is the start of this induction, the level 0 current. Mm-hmm. Yeah. I mean, here I want to use the assumption that I made, so of course there can be more complicated situations. So
This construction clearly using the fact that you are in dimensions.
yes.
In higher dimensions, there would even be a problem writing down the J1 because one would have known.
Exactly.
But now there are these higher form symmetries that people talk about where the charges don't live on 4-dimensional manifold but rather have 4-dimensional manifolds.
Mm-hmm.
So there the notion of integrability is generalized in some way in those higher forms.
I don't know. From my point of view, this is really a very special property in 2 dimensions that you can formulate this. And there are some comments also in the context of n equals 4 where maybe in an appendix of this paper by Dolan, Napi, Witten or so, or just by Nappi, where they comment on possibilities to generalize this, but I don't think there's a solution to this problem. Yeah, and this is also what.
Because the germ sentence matter theory that again is very clear. I talked to Chirag, he seems to see that there are some uses of integrability. That's why I thought.
Well, but in N=4 you also have integrability in higher dimensions, right? It's just enters in a very special way. Yeah. You have to find the two-dimensional embedding in this 4 dimensions, is my impression. Okay, let me just introduce one more important quantity in the context of integrability. And well, here you've seen I can construct this tower completely without this spectral parameter. So it will really just be an auxiliary quantity that I introduce here. So the idea is to find a generating function for my tower of conserved charges. And well, I want to write an ansatz in a particular form. That's just due to the convention. So I don't write the expansion of t of u, but of the logarithm in principle formally. So I should have an x of what I write down. It's just in principle it would just be a reordering of the charges if I drop this, but for conventions let me write it like this. So suppose I could write down a generating function of this form. This would be a nice thing to have. And in order to get this, I modify once more my covariant derivative. And I make it dependent on a spectral parameter. So I write it as this plus a quantity L mu, which is my so-called Lux connection. And in this particular context with these currents here, I define it in this way. You might also differently parameterize the spectral parameter, but here this is a convenient way to parameterize things. Yeah, so I introduce a covariant derivative with this connection here, and now I can formulate the flatness and conservation simply as the vanishing of this commutator for arbitrary parameter u. Sorry, this will depend. These are the charges, yes. I mean, I've integrated out the x, yes. No, this will again act on my currents. Yeah. So you see, this is the statement. These are small j's. These are my currents. Yeah. So they will act on the currents. Yeah. And the fact that these two covariant derivatives commute can also be understood as the compatibility of a particular so-called auxiliary linear problem. Which is this differential equation. So I have some auxiliary function x, and this should be 0. And in order for this, here I have these two components. In order for this to be compatible, if I act with a second derivative on it, then these two should rather commute to have a yeah. Thanks. Exactly.
Why do you need this 1 by 1 minus h squared to get
It's just changes well, it changes in the end the expansion of this quantity, so it changes what I call my charges. And I want to end up with the same charges that I introduced before, the same structure. I mean, I could reorganize the charges. I could take linear combinations or similar things, and still they would be conserved, right? So I have to agree on some basis of charges. What do I call level 0? What do I call level 1? In order for this to come out right, I introduce this particular prefactor. So this is the auxiliary linear problem behind this compatibility condition, and it's really auxiliary. This phi, in this context at least, has no physical interpretation. And the solutions to this equation at points x0 and x are now related by a transport matrix T. So my solution at t comma x u is this transport matrix T x0 x u phi of T x0 u. And this transport matrix is nothing but the path ordered exponential of such an integral here. So I take the one component of my Lux matrix and I integrate it, which will have the correct properties to transport these solutions here in this way. And now the quantity that I'm actually interested in is the transport along the whole axis, which is again my monodromy. And maybe I write it down here.
what is the point of looking at this problem?
Sorry?
Can you explain the point of looking at this particular problem?
Well, one thing is to motivate why I consider this quantity t, which will be interesting for the reasons that I now write down. And yeah, the other thing is to give an interpretation to this equation here. Why yeah, you don't see it anymore. There it was a commutator of the two covariant derivatives that vanished, and well, because if I act with a second derivative on this and the two don't commute, then my solutions will not be unique, right?
Ensure that there is a phi t of x which exists because that's the integrability condition also. So we apply the mu first and then mu first. The point here is that how this wants to be by construction. That phi is given by some Wilson line, I x, x naught. But
it's not clear to me. Well,
There, there should be in classical HPGC, there should be an infinite number of action variations.
yes.
There should be an infinite number of conserved charges in evolution. And here you seem to have constructed some flat,
Yes.
Flat objects. So
Yes, in principle, I should study the charges and see whether they are in involution. I guess people have done this somewhere, but I.
This action angle one has local concept contribution, right?
well, you can have some weird kind of parameters in the phase space, and in which given some, you're not saying anything about what the original variables of the Lagrange are. So all you need is that there should be an infinite number of action variables which are
Right, but as I understood this Yangian proof, all these high quantum currents, they are bilocal and trilocal in nature. They defined at three different points so on. While the conserved charges of the integrable model, like the Hamiltonian, the second Hamiltonian, the third Hamiltonian, so on, they're still, even though they're slightly long range, they're still local, right? So that's why it was immediately to the point. Maybe
Well, yeah, in general, often you can reformulate this in terms of local charges, and this just corresponds to, taking maybe a different expansion of your monodromy or transfer matrix. But okay, let me first write down what the expansion of this monodromy here actually is. Yeah. So if I look at the transport along the whole axis, so I go from -infinity to infinity, then I find this monodromy. Well, here I still write the dependence on T. But the important point is that what I get now is exactly this expansion in terms of my tower of conserved charges. So here I have this plus higher orders. So you see that this naturally connects to the previous case. And well, in order to have this particular expansion, I introduced this prefactor also in the in the Lux connection. And yeah, since this is just an expansion in conserved charges, actually the monodromy is time dependent. Again, if I assume that the current is 0 at spatial infinity. So here, just assuming these two very simple things, namely the conservation and the flatness of the current, one sees that one can derive this tower of charges, and you've seen that in principle I didn't need the spectral parameter. I can also construct them without, but it's convenient to have a spectral parameter because it compactifies things. This monodromy is just a compact object to think about these quantities. So let me just give a particular example because so far it was quite abstract. I assume the existence of some current, and an example is the chiral Gross-Neveu model. Which is a 2D QFT for interacting fermions, and it's actually classically conformal, and the fermions get masses via quantum corrections. So let me write down what the Lagrangian is. here I have my spinors, coupling constant, and these TAs here are now some UN generators. And here I have Dirac spinors. Psi, so this is a two-dimensional model with a UN symmetry. And I can compute the equations of motion from this. And using these equations of motion, I find that the following current J mu, so here just again for conventions I use these particular prefactors. This current then can be shown using the equations of motion to be conserved and flat. Yeah, so that's a relatively simple model which has a Noether current associated to this UN symmetry, and the equations of motion tell me that this conservation and flatness for this current is actually obeyed. This is classical at the moment. At the moment it's classical, yes. Right.
Where do you use the Franklin structure?
Well, maybe I comment on this later, but for example, this product of currents here will become singular in the quantum theory. Well, so yeah, from this I simply get infinitely many charges using this construction. And just 2 comments. Actually, for this particular model, it seems not to be clear whether or how one can formulate these higher charges as Noether symmetries. So even though it's a rather simple two-dimensional model, so sorry?
So the construction gives the currents associated to the higher charges.
I construct higher currents and higher charges, but I don't know how to relate them to a symmetry of the Lagrangian. I know this for the first one, but not for the non-local ones.
I mean, if you just take those charges and commute with the basic theories of the theory, like fermions and so on, so you don't get back. That's right. I mean, if you take any of the higher charges and commute with the psi and so on,
In particular here, this is
you will not get back the psi. Is that the point?
well, even for this one, I need the equations of motion to show the flatness. Yeah, so
take the equation of motion, so take an also current, and
yes.
so here, for example, for the zero level current, okay, I mean, we know that it's simply rotates. If you take this J and act on this psi, it will just multiply.
I don't think you get the right quantities. And in principle, what you would like to have is an off-shell symmetry, right? To go through Noether procedures. And for that, I think you even have to. There are one or two examples where people could formulate these non-local charges in a two-dimensional theory. What was it? Probably also the sigma model. As Noether charges, but to write it as an off-shell symmetry, they already had to write down an off-shell version of the current. So the currents, the non-local currents that I've written down here are on-shell currents in some sense. So even in
before this, you were assuming that the symmetry is there's an off-shell discussion, right?
but for the flatness, I need the equations of motion.
But for something to be the symmetry, you need the symmetry of the off-shell line.
Yes.
So how is that guaranteed then? If you're using equation of motion in this case?
Well, it's guaranteed only for the level 0 current here. I mean, the level 0 current is conserved.
Sure, but level 1,
I don't know how to write this as a Noether charge. That's my statement. I don't know what the associated symmetry of the Lagrangian is, or whether it exists.
is it clear that it exists once?
I guess not even that's clear, no.
Because that current is not conserved off-shell, right?
Yes.
So what does
No, you need the flatness. For the higher currents, you need the flatness, and for these, you need the equations of motion.
higher currents are conserved on-shell?
On-shell, yes. On-shell, yes.
But there is no off-shell symmetry that you can associate.
Yes. I don't know it. there, yeah, there may be one, but I don't think it's known.
Right, so I can show equation motions are inherent under or inherent under those consumptions. That I can show. Not the action, but the equation of motion.
Probably yes. I don't think people have written down the transformations, but probably you can show this, yes.
And just to make sure, suppose I construct this symmetry. I understand it's a formal construction maybe, but what do I gain for this model? Do I gain more? Can I solve something which I was not able to solve earlier?
Well, what you can
At the classical level.
at the classical, well, what do you want to solve?
I mean, at the classical mechanics, I know integrability or all these things. If that equation of motion becomes first order, then I am able to solve the whatever. So here with this, what exactly? How is it exactly helping?
I guess the main interest here lies actually in the quantum case, that you have similar charges also in the quantum case, and then you can, for example, constrain the S matrix of the theory. I guess you can also use integrability to construct classical solutions. I haven't tried or thought about this explicitly, but in principle this should be possible. So I think this is generally not clear. As I say, for some particular models like the sigma model, one can do this, but for this model, for example, I don't think it's clear. And the second thing is what I wanted to say is that the Poisson brackets for this theory. So if you now sit down and evaluate the Poisson brackets for these conserved charges, then they show the structure of a classical Yangian that I want to introduce in the next part, and that's why this is interesting for this particular lecture. So this is the connection. So you already have seen yesterday in the talk these bilocal symmetries, which look very much like these integrals here. And I've shown you how to generically construct them. And this is a particular example where the Poisson brackets also give you the same algebraic structure that you have for the Yangian. And what the Yangian explicitly is, I will give more details on this in the following. Yeah.
This is two-dimensional, right?
This is two-dimensional, yes.
And here you get a infinite dimensional algebra, right? So
Here it's classical at the moment, yes.
Classical. So this model is conformal, right?
At the classical level.
At the
yeah.
classical level. Is there a map between two-dimensional conformal algebra? Like it is also infinite dimensional.
I don't know. I don't know if you can. Well, I doubt it because the conformal symmetry is broken at the quantum level, but this will not be broken in the quantum theory.
So are you saying, suppose in two dimension, I can use this one not here if they are same on I mean, is it clear they are not the same?
No, it's not clear to me that they're not the same.
Yeah, basically, right? These are global symmetry values. Right. But that's some position. But is there some non-linear map or some kind of map that I can
Yeah, well, it's hard to exclude this, right?
I'll tell you, there was a paper by so two-dimensional high-spin symmetry. It's a infinite dimensional algebra.
Mm-hmm.
There was a map, and then people constructed similarly Yangian algebra. And there was a map. There was a non-linear map at least.
Gabardil and
Yeah.
something, yeah.
I was just asking.
Okay, but now you are asking whether there's no.
So Claymore, so I have a higher spin algebra, and then they constructed a Yangian algebra.
Yeah, I think they have this W algebras there, and they find a Yangian in this with a very specific map.
If there is a W algebra, is it can be related to the Yangian algebra or not? They try to.
I know the W algebra part of the story, but I don't know the Yangian part. So there is some relation.
At least up to 3 levels.
I think they have 2 papers on this, maybe from last year or so. Okay, so this was my classical motivation for the Yangian. So let me now come to what the Yangian algebra actually is. And well, in order to approach this, maybe it's also good to understand where the name actually comes from. So I want to start this with a discussion of Young's solution to the Yang-Baxter equation. So, well, I think this was in 1967, where Young looked at the quantum mechanical Hamiltonian of this form. So some particles with a delta function interaction, and he tried to solve the Schrödinger equation for this and made an Ansatz in form of a Beta Ansatz for the wave function. So this looked like this. He looked at a particular regime where the particles are in this order, and he wrote down some ansatz in terms of such plane waves. So here I have I have some indices. These are the momenta and the coordinates. This is a matrix that has where the matrix indices here are actually the sets of all the ki and the sets of all the ji, and the sum here is overall j1 to jn, being permutations from 1 to n. So this is an n factorial times n factorial matrix. And well, yeah, in the standard way, he looked at the Schrödinger equation and imposed these conditions that the that the wave function at the points where two of these coordinates coincide has to be smooth, and similarly for the sorry? Sorry, this here should be K1 to Kn. Yes. And what he found was, just schematically, he found that these conditions 1 and 2 require that swapping rows of this matrix M comes with a particular factor RAB, where A and B now labels the rows in this factor. Has to satisfy this particular equation. I will tell you what this R is in a bit. So this factor has to obey this equation, which is known now as the quantum Yang-Baxter equation.
What do you mean by x and x
Here,
here?
I mean the coordinates. So I don't write all the labels, just single ones.
Permutation processes, right? A labels one permutation, B labels the other permutation.
No, well, in principle, I should write the sequence of arguments here, and this is where I'm at the point where two become the same. So now I don't have this order. It's exactly the
Where one pair is swapped.
yes.
And we are related by swapping one pair. Those are the labels what you
Yes.
have.
Yes. So yes, I will tell you this. So here in this equation, Uij is just the difference of momenta, yeah, of these particles. And the explicit solution that he gave for this vector RIB of Uij takes this form. So C here is just a constant. And here I have the identity on A and B, and here I have the permutation operator on A and B.
In that equation, Pi means Pji, or do you mean Ji equal to that?
Here? Oh,
You define a momenta in a particular way, right? So you, I don't know, is the I index the particle index or the permutation index?
this here is a particle. This is the momenta of the particles I and J.
I is the particle index.
Yes.
Because particle index is different. I might correspond with different Gi in different rows.
I mean, this I you mean, or no?
The P's and X's have different type of indices, right? One has the P has a J and the X has a K.
Yes.
Where K labels particles and J labels some fixed
Ah.
momenta.
Okay.
So now that is K type or J type?
J type.
Yes.
Yeah. Right. But in principle, it's just labeled, right?
So it's a label of the particle.
Yes, but here, I mean, it's just Uij is just a shortcut for this difference. So
So it matters because you're looking at different rows, right?
it might.
It matters because you're looking at different rows. There's some swapping three rows in different order.
This exactly.
Yeah.
This is the
The
exactly.
point is that if I is not a particle index, but these things mean different things if I is a particle index, a K type index or a J type index.
Okay, you want the interpretation. Okay, I see. Mhm. I see. Here I just mean that I define the symbol Ui minus J to be this thing. Okay, this is called Yang-Baxter equation. Yang comes from exactly this analysis, and Baxter found a similar equation in the context of vertex models. That's where the name comes from. And the solution that Yang wrote down has exactly this form. So for this particular problem, so let me just make one comment. I mean, this is a bit specific because I have a permutation operator. Just if I want to generalize this, so for example, for G, for an algebra G being UN, the tensor Casimir operator. So if I have generators JA of this UN and I compute the tensor Casimir, then this is exactly the permutation operator, yeah? So this here is the tensor Casimir of this G. I just do this to motivate that what I now want to call Young's R matrix and what people in general call Young's R matrix is this object. You don't see it? I don't say it's clear, but for example, you can take the Pauli matrices here and do it explicitly. I just tell you what comes out is the permutation operator, and that's why it makes sense to replace in this definition of Young's R matrix this by a tensor Casimir, because then I generalize this to some arbitrary algebra. Yeah, and yeah, this is known to be the simplest solution to the quantum Yang-Baxter equation. Yeah, this is Young's R matrix that plays a very important role.
So Yang actually is in delta person against anyone, right? It's completely automatic question, right? Do you know if there's in anyone's there's an analog of the U12 sort of variable?
Well, you have spectral parameter dependent and spectral parameter independent versions of this equation. Yeah, in fact, it turns out in many different contexts. I don't know if there's also a deformation of your problem where you can introduce such a parameter, but yeah, it can also well exist without the spectral parameter. Sorry? It's just an example. So let's say example. I just want, okay, in this particular model, what Yang wrote down in his paper is this thing with the permutation operator. I just want to say that if you want to make connection to an underlying algebra, then for UN, the permutation operator can be rewritten as a tensor Casimir. So what I now want to call Yang's R matrix is not this thing with the permutation operator, but this thing with the tensor Casimir. Because then I have written down Yang's R matrix with an underlying Lie algebra. I can now forget about UN and just write on Yang's R matrix for any Lie algebra and write here the tensor Casimir. That's what I wanted to say.
But for UN, I can just say P also.
You can also write P, yes. I just want to show how the algebra enters into this thing. Yeah.
So for the E to the UN, what is the corresponding quantum mechanics problem? I mean, so you started with this hard-coded partition problem of partition from a line.
Yes.
So there I understand.
For example, the S matrix in this Cairo-Ross-Neveu model would be something like this.
So are you saying that the auxiliary quantum mechanics is a problem?
No, it's not auxiliary. It's really the. Oh.
I mean, how do I get to this?
In
From, starting from the first row.
the two-particle S matrix will obey this. R will
And the E12 would be what there?
rapidities, difference of rapidities. Okay, this thing is very important, and it's actually the motivation why the Yangian is called the Yangian, this quantity. Before coming to this, I have to give some.
Sorry. So this is this general theory of the Abundancy code about factors in the distance, in which all 4-point functions are just straight. So e to the power I delta, and where delta is the function of the rapidity.
All 4-point function, you say?
I mean, two going.
2 going to 2 is described by this process. And yeah, as you say, this is, well, the picture behind this is this, right? So you can, it's a 2-particle scattering, but as a whole thing, you can consider it as 3 to 3 particle scattering. And this is the statement in a S matrix theory about factorized scattering.
This equation still allows a non-trivial two-body scattering. It's a matrix, not just a field. So it's an equation on the matrix.
Yes. The point is everything can be expressed in terms of the 2-particle S matrix if you have factorized scattering. Yeah. And since there are 2 ways to do this, either like this or either like this, you need for consistency that this equation holds. And yeah, actually this is probably the most important equation of quantum integrability. It's not so easy to define what it means, but probably the best definition is that if you find an object that obeys this equation, then you have a quantum integrable system in some sense. So yeah, this is a very important equation.
So the system may have higher temperature, then you always discuss into 2-to-2 section.
In particular theories, in integrable, this means integrability, that you can do this in two dimensions.
In 2 dimensions.
In 2 dimensions.
Not in high dimension. The same system doesn't do it.
No, it's not the same in higher dimensions. No.
Because the light will be correct. So the question we're asking is saying that suppose I can construct high point function in terms of lower point function. The 2-to-2 stepping. All the high point functions I can construct as a 2-to-2
Now
stepping.
we're talking about amplitudes, yeah?
Are you talking about H matrix? Right?
Yes.
So all the high point H matrices, suppose I can write in terms of 2-to-2 stepping. Is it a criteria or there is something more to it? Like this implies that, no? Yeah, as you said, at least in 2 dimensions. This condition implies that all the high point functions can be written as
This condition?
right.
No. This is just a consistency condition for this to be possible. It's not clear that this also implies that the S matrix has to factorize. There could still be an honest 3-to-3 particle S matrix which does not factorize in a theory, while this holds, I mean, hypothetically, while this holds for the 2 particle S matrix.
Do you know that this is
I guess no. But
So, what I had in mind, suppose this year rule was, say for this year rule function for some theory. So I write down higher point function in terms of lower point function, say 2-to-2 stepping. Is it also same as, I mean,
well, I think this is rather different here. Yeah, certainly. I mean, and this is really 2-dimensional, what I'm saying here.
right.
It's a property of 2 dimensions. For example, yeah.
Does it mean that no theory will say the 6-point vertex is electricity?
No, say again? No?
Does it mean no theory with the 6-point vertex is electricity?
Well, or integrable in a different sense. In 2 dimensions, you mean? So,
I guess that you would have relevant operators.
well, okay. Now that we understand that there is this important quantum Yang-Baxter equation and that this thing here is called Young's solution, let me just introduce some notion of, so this is called quantum Yang-Baxter equation. Let me just say what the classical version of this would be. And for this, I want to assume, so I want to introduce a parameter h bar, and I do this by assuming that 1 over u goes as h bar, yeah? So I simply set 1 over u to h bar times 1 over u, which means now that that r of u and h bar is 1 plus h bar times some quantity r of u plus, in general, possibly higher terms. Yeah, this is a special solution in this model. And here I've introduced this small r, which is then known as the classical R matrix, while this is the quantum R matrix. And now one finds that the quantum Yang-Baxter equation for h bar going to 0, if I just keep the order, h bar turns into what is known as the classical Yang-Baxter equation. So this is the classical Yang-Baxter equation. Yeah, and in principle, if one has time, one can also relate this classical Yang-Baxter equation to the problems in classical field theory that I've shown you before. So the important thing about this classical Yang-Baxter equation is that there are some interesting theorems by Vilavin and Drinfeld. And well, I don't spell them out in all their mathematical explicitity. I just give an essential version. So these are theorems from 82 to 84, where these things are treated. But essentially, the statement is that the solution R of u to the classical Yang-Baxter equation can be classified via the lattice, so some subset of the complex numbers of their poles in the complex plane. I don't have to write this out, I guess. And it turns out that there are only three different types, namely rational solutions to this problem, where the rank of this lattice is just 0, so it's just a point. Trigonometric. And elliptic solutions. Yeah. So here I have a single pole, here I have a line, and here I have a
The R of this shouldn't it necessarily be 1 over u? Shouldn't it go 1 over u? How are you introducing x bar? You said x bar is to be introduced just by replacing u by u over x bar, right?
yes.
Then if you expand in the power for the x bar, then clearly the R of u would only have 1 over u dependence. R squared will have 1 over u squared and so on.
In this particular case.
Well, I thought that would be your general thing. The way, first of all, I need to understand how you are introducing x bar.
But
The description that you gave
here
was
here
to replace-
I do it like this. Okay.
How do I introduce x bar in a general R?
How do you introduce?
Because if I do it that way, then
No,
I will
you
always get rational.
you don't do it that way in general. You do it that way here. In general, you consider an expansion in h bar, I guess, and try to solve the assuming some conditions. This is an R matrix for a particular model of rational type. So this is here exactly where Young's R matrix belongs. Yeah, and this was just to motivate how I can get to the classical Yang-Baxter equation from the quantum Yang-Baxter equation by doing this rescaling. And everything about the Yangian exactly corresponds to the quantum deformation of this classical case here, number 1, namely the rational R matrix. And that's why it's called Yangian, because the simplest rational solution is this one of Yang.
What is classical Yang-Baxter? How does it appear? I mean,
Yes.
giving the example of what is that?
Okay, the classical R matrix will enter, if you, for example, if I would study now further the classical Gros-Neveu model, and I would look at the Poisson brackets of the Lux matrices, then the classical Yang-Baxter equation will enter into some expressions for the Poisson brackets there, and play an important role. So if you look at classical models, this also plays some kind of role as of a, well, structure constant maybe in the same sense as yesterday I told you about these RTT relations. I might make more comments on this later here. I mean, yeah, there's a lot of theory also behind these classical systems, and well, you would have these Lux matrices. You would have to understand what the Poisson brackets are in your particular model. You have to evaluate them.
So I have some infinite hardcore repulsions. So classically, they would just stay put. If I have some order of particles and I have this infinite hardcore repulsion, then the orders will never split. Has it, and quantum mechanically, the wave functions have, because what you
Call it semi-cluster.
semi-cluster.
Because that one is like that. What you're saying.
One is like that. Yeah,
And
so
this
I
is
was
some,
wondering whether this
one
H
look
bar,
at that.
yeah, this H bar is something like 1 over C, where C was the strength of the delta function. Where, yeah, may I just want this? Yeah, so this one is like that, I think. The one is like the infinite strength delta function, and nothing happens. Just so many boxes.
What is the difference given in the system? What is the difference?
When the functions are in opposite, I don't know how to
So you want the physical interpretation of the classical R matrix in the delta function problem.
yeah. So in particular, I want to understand that one.
This one is Newman calculated, right? So when you draw something happens.
One is that.
One should be the fact that things don't pass to each other.
Yeah, I think one should be the classical limit could be that they just come bouncing back.
No, so then it's a hardcore thing. If you're just writing a Hamiltonian sum over rho I square, then it is fast to equal. This is what R1 2 equals 1 to, right? That you can exchange.
No, but why is the classical limit absence of the
That doesn't mean
Okay, I'm talking about non-differentiation problem. Sorry.
Oh, no. I meant that in the problem, see, I can understand the R matrix, I mean the quantum Yang-Baxter equation, the way he nicely got it from the hardcore repulsion on the line, and that corresponds to all this stuff. And I just wanted to say, in that model, yeah, so classical would simply mean that it just sees the delta function, it just bounces back. And that would somehow mean that one. And then there is some possibility of a little bit of tunneling across the delta. This is the kind of understanding that I was looking for.
No, I see. It's an interesting point to work this out explicitly. I haven't done or seen this, yeah.
And there I can understand that the little r is like at the edge of the element, because and then things which were like product stuff now it become
Something in a completely different
Well,
not classic what
No, the way this solution is given by a particular ordering of particles, and then telling you what happens if you change path. Already.
Sure.
If you switch 1 and 2, what is the additional phase that you should get?
Right. But in the case where there's no interaction, why I'm saying that all the different permutations, the sums of permutations, all of them would be the same thing, right? Like it should not depend on permutation. In the case when there's no interaction. There's like n particles of n different ones. It doesn't matter what order you use.
Yeah. But I think in this language it's not really.
No, it's not. It just means that when you exchange two permutations, so there's two rows of the matrix, you don't get a pair. It's permutation change.
well, I guess, yeah, we can. Actually, I thought, okay, it's already quite late. Maybe this.
Total transmission versus total reflection. That's the question being asked
Mhm.
about that. So the total, what is the total transmission S matrix and what is the total reflection?
Yeah, that's again.
Mhm.
So the point I was trying to highlight was that this H bar is not a real H bar. It's just a formal thing that usually we say.
Here it's a formal thing,
Yeah,
yes.
so like
No, but
particular
what
set
is,
theta-
how does that make sense of H bar square?
that is
I mean, one way to interpret this H bar is just to remove the 1 and whatever this is the quantum. Whatever it is this small r. That's one way to if there is no specific way to introduce H bar, then how do I understand H bar square term? Is there any H bar square term, let's say, for trigonometric models?
Well, this is just this. Actually, the idea, and that's what I will probably tell in the next lecture then, is that Drinfeld now wanted to start with this thing and construct general rational solutions as expansions around this. So these should be the first two orders. And what happens now if I switch on higher orders in H bar? Solutions to the quantum Yang-Baxter equation. Yeah, and you see the first order here is expressed as a tensor Casimir of a Lie algebra generator, yeah, which is the level 0 generator. So this is how you come to the Yangian. The question is, how can I express the higher orders? And this is how the Yangian will enter then. But yeah, I guess this is a good point to stop, and I start with this in the next lecture.